Dear students, I am Dr. Mukeet and I welcome you all to the lecture number 28 of Electronic Devices and Circuits. Before we begin chapter number 5, let me provide the summary of topics that we learned in the DC analysis of BJTs in chapter number 4. The topics under discussion in our previous lectures included DC analysis of various BJT configurations, including fixed bias configuration of BJTs, emitter bias configuration of BJTs, voltage divider bias configuration, collector feedback configuration, emitter follower configuration, common base configuration, and finally we learned how to design different BJT circuits. In chapter number 5, our goal will be to become familiar with RE, hybrid and hybrid pi models of BJTs. We will learn to use the equivalent model to find the important AC parameters for an amplifier. We will understand the effects of a source resistor and a load resistor on the overall gain and characteristics of an amplifier. We will become aware of the general AC characteristics of a variety of important BJT configurations. And finally, we will learn about the advantages associated with the two-port systems approach to single and multi-stage amplifiers. We will now learn about the AC response of BJTs by reviewing the most frequently used models to represent the transistor in the sinusoidal AC domain. The first thing that need to be considered in the AC analysis of transistor networks is the magnitude of input signal that can be classified into small signal magnitude and large signal magnitude. Both input signals have different techniques by which their circuits can be solved. In this chapter, we will only deal with the small signal techniques. There are three different models that are commonly used in the small signal AC analysis of transistor networks, including RE model, hybrid pi model, and the hybrid equivalent model. In this chapter, we will discuss about all of these models, but our emphasis will be only on the RE model. We discussed in chapter number 3 that the transistors can be used for the purpose of amplification. Simply by amplification we mean that the magnitude of input AC signal increases after passing through the BJT, or in other words, the power of output signal is more than the power of input signal after amplification. Here the question arises that isn't the stated definition of amplification violating the law of energy that states neither energy can be created nor it can be destroyed, but it can be converted to other forms of energy? The answer to this question is that amplification does not violate this law because the power of output signal increases due to the addition of DC power sources. Now let us discuss about the BJT modeling, that is the most significant aspect of learning about the small signal analysis. We can define a transistor model as a combination of circuit elements properly chosen that best approximates the actual behavior of a semiconductor device under specific operating conditions. Once the AC equivalent model is determined, its circuit can be used in place of that transistor. You should understand that the whole purpose of replacing a transistor with its equivalent model is to solve the transistor containing circuit by applying simple circuit analysis techniques. In the early years of a transistor, hybrid equivalent model was most frequently used, in which an analyst was just required to put the given values of different parameters to solve an electronic circuit. But it had a drawback that this model was applicable for only a certain set of operating conditions that might not match the actual operating conditions. However, if you still see the data sheet of a transistor, you will find that the manufacturer do list the parameter values of hybrid equivalent model, so it is not completely avoided. As a replacement for hybrid equivalent model, RE model has become the more desirable approach due to its high accuracy. However, it also has a drawback that it does not include a feedback term, which can be important in some cases. RE model is the reduced version of hybrid pi model that is usually used for high frequency analysis. Our main emphasis will be on learning the RE model in this chapter because by thoroughly learning one model, transition to other models will be an easy task. Now let us assume a circuit on which we can apply the basic steps of doing AC analysis of a BJT based network. The circuit is shown here. As we are only interested in doing the AC analysis of the given circuit, so the first step is to remove all DC power supplies and replace them with zero potential or short circuit. DC supplies only determine the DC level of the output voltage and has nothing to do with the magnitude of AC output. The next step is to remove the coupling capacitors C1 and C2 and bypass capacitors C3 or replace them with short circuits. After following these two steps, your circuit will look like the one as shown in this figure, in which you can clearly see that all the DC supplies and capacitors have been replaced with their short circuit equivalents. While doing the AC analysis of BJT circuits, we will always focus to find the values of few important parameters whose list is provided here. These important parameters include input impedance from base to ground, Zi, output impedance from collector to ground, Z0, input current or base current, II, and the output current or collector current, I0. We have not yet discussed about the RE model of a BJT, but these steps are necessary to perform before starting the AC analysis. You should keep this general diagram in mind while performing the AC analysis of any network because the direction of currents and polarities of voltages are very important and key aspect while solving these circuits. As you can see in this diagram that the direction of input current II and the output current I0 should be such that they are entering the system. If you come across a system with any of its current leaving the system, you must attach a minus sign with it. The polarities of VI and V0 are also shown in this diagram. If any system has a different polarity, then a minus sign must also be assigned to it. If we establish a common ground and rearrange the elements of the circuit shown on the previous slide, whose AC analysis circuit is again shown here, by making the ground terminal common and rearranging the circuit elements of this circuit, we can redraw this circuit as shown in this diagram. Here you can see that R1 is in parallel to R2 and RC will be the only resistor at the output side as RE has already been replaced with a short circuit equivalent. Before formally beginning our discussion about the RE model, let us summarize the steps of drawing AC equivalent circuit. Replace all DC sources with short circuits. Replace all capacitors with short circuits. Remove all elements bypassed by short circuits. And finally, make the ground common and draw the circuit diagram again in a more logical manner, like the one shown here. Now we will discuss about the RE transistor model for the configuration of common emitter, common base, and common collector. We will also discuss about each approximate circuit of RE model, that why is this a good approximation to do actual behavior of a BJT. First of all, let us discuss about the RE model for a common emitter configuration. You should keep this thing in mind that the RE model of a common collector configuration is same as that of a common emitter configuration that is to be discussed now. Starting with the input side of the common emitter configuration, we find that the applied voltage VI is equal to the voltage VBE, with the input current being the base current IB as shown in this figure. We need to develop an equivalent RE model for the AC analysis of a BJT connected in the common emitter configuration. I'm talking about this transistor that is connected here in common emitter configuration. We need to find the equivalent RE model for this transistor with the help of its input and output characteristic graphs. For this, we need to discuss the input and output characteristics separately. The input characteristics appear as shown in this figure, where it can be clearly observed that it implies the behavior of a forward bias diode. I'm talking about this input characteristic graph. As you can clearly see that this graph is representing the behavior of a simple semiconductor diode. Therefore, we can easily put a diode as a representation of the input side of this configuration as shown in this diagram. Now let us discuss the output characteristics to find the equivalent circuit of output side for AC analysis. By drawing the characteristics of collector or output terminal, we take an assumption that value of beta is constant as shown in the characteristic graph of this transistor. The graph of output characteristics with a constant value of beta shows that the output side of this configuration can be represented by a constant current controlled source with a magnitude of beta IB. After replacing the input and output parts of the configuration with the appropriate circuit elements, now we are in a position to draw the equivalent network for the whole common emitter configuration as shown in the diagram, with a diode at the input side and the constant current control source at the output side. This equivalent model can be further simplified for the AC analysis by replacing the diode at the input side by its equivalent AC resistance that can be determined by the level of emitter current IE as shown in this figure. By using the discussed equivalent model, we can calculate an important parameter required for the AC analysis, and that is the input impedance ZI. The input impedance can be calculated by using the formula of ZI is equal to VI over IB. As we know that the input voltage VI is equal to the voltage between base and emitter terminal, that is VBE. Therefore, we can say that ZI is equal to VBE over IB. Now by solving for VBE, we can easily derive that VBE is equal to beta plus 1 times IBRE. By replacing the value of VBE in the formula of input impedance, we get ZI is equal to beta RE. These steps are quite clear that first of all we have cancelled the base current IB and replaced beta plus 1 with beta. I'm talking about these two currents IB in the numerator and denominator. Simply cancel them both and replace beta plus 1 with beta because the value of beta is quite higher than 1. If you do both these things, then you get the final formula for input impedance as beta RE. After performing these simplification steps, finally we get the most simplified RE model of the common emitter configuration for performing the AC analysis. The improved BJT equivalent circuit looks like the one as shown in this diagram. It has only two components, including a resistor at the input side and a constant current source at the output side. Both input and output are isolated but are only connected through a current controlled source. As you can see that the magnitude of current controlled source is beta IB, and this IB is the current of input side. So although these are isolated with each other, but still they are connected with the term IB. In order to include the effect of output impedance, we need to consider the typical output characteristics graph of a BJT as shown in the diagram, with VCE on the x-axis and IC on the y-axis. By using this graph, we can include the non-ideal behavior of a diode and can achieve an even closer characteristic model of a BJT for AC analysis. Right now, we have considered that the value of current is constant due to constant value of beta, but actually these curves are not constant. They have some slopes associated with them, as we will discuss on the coming slide. Earlier we assumed straight lines, rather they have a slope as shown in the output characteristic graph that defines the output impedance of this device. The steeper the slope, the less will be the magnitude of output impedance Z0 and vice versa. You can notice in this diagram that all slope curves are extended until they intersect the horizontal line. Interestingly, all the extended lines intersect the horizontal axis at a common point that is known as early voltage and is represented by VA. It can also be seen from this graph that as the value of base current IB increases, the output impedance Z0 also increases, and the same is true for the collector current IC. After this whole discussion, the output impedance can be written as R0 is equal to del V over del I, which defines the slope of these curves. Usually, the value of early voltage VE is sufficiently larger than the applied voltage VCE. Therefore, the output impedance can be written as R0 is approximately equal to VA over IC, where we have ignored the effect of VCE, as VA is quite larger than VCE. For situations where the value of early voltage is not given, the magnitude of output impedance can be calculated by R0 is equal to del VCE over del IC, where VCE is the voltage of x-axis and IC is the current of y-axis. The output impedance can now be defined as a resistor R0 in parallel to output as shown in the equivalent circuit diagram. Here, as you can see that we have connected a non-ideality factor by R0 in parallel to beta IB that was earlier defined. This equivalent circuit diagram consisting of three components including input resistor beta RE, controlled current source dependent on the base current, and output resistor R0 connected in parallel will be used for the AC analysis of common emitter configuration throughout this text. The equivalent circuit for the AC analysis of common collector configuration is similar to the one discussed for common emitter configuration, so it will not be discussed separately. However, now we will discuss about the third most important configuration of a BJT, and that is common base configuration. The general input and output characteristics of the input and output circuit will generate an equivalent circuit that will approximate the actual behavior of a BJT connected in common base configuration. Just like the input side of a common emitter configuration, the input side of a common base configuration can also be represented by a forward bias diode, and the output side can also be represented by a controlled current source, but the difference is that the direction of current in this controlled source is opposite to the one as discussed for common emitter configuration. Phase shift between the input and output voltage of a common base configuration will be 0 degrees. Before discussing about the phase shift, let me clarify that in this diagram we have replaced the diode with its equivalent RE AC resistance. And after discussing this, we can say about phase shift that it will have a 0 degree difference between the input and output voltages for common base configuration. Unlike common base configuration, the phase shift between the input and output voltages of a common emitter configuration was 180 degree. Now we have discussed all the transistor models for the most basic configuration of BJTs. We are in a position to discuss various networks of BJTs for the AC analysis based on these models. The first configuration to be analyzed is the common emitter fixed bias network as shown in figure. In which the input voltage is applied to the base of the transistor and the output voltage V0 is associated with the collector terminal. Here you must observe that the input current II is not the base current IB, but it is the source current, while the output current I0 is equal to the collector current. In order to perform the AC analysis, we will redraw the given circuit by removing all DC supplies and replacing capacitors C1 and C2 with their short circuit equivalents that will result in the circuit as shown in this figure. It is important to mark all the important parameters of AC analysis, including ZI, Z0, II and I0, as shown in this diagram of redrawn circuit. The next step is to substitute RE model of the BJT that was discussed for the common emitter configuration. After replacing the BJT with its RE model, the network looks like the one as shown in this figure. As you can see that we have clearly replaced the transistor, the BJT, with its equivalent RE model. This blue box is showing the equivalent of a transistor, in which we have connected those three electronic elements, including beta RE resistor at the input side, controlled current source in parallel to the resistor R0 at the output terminal of a transistor. So overall, this blue box is representing this transistor. The rest of the circuit is the same. RC is connected still at the output terminal and RB is connected still at the input terminal. Now we can easily find the formulas to calculate the values of important parameters of ZI, Z0 and voltage gain for this configuration. It can be clearly seen from the final circuit diagram that the input impedance ZI can be calculated by the formula of RB in parallel to beta RE. Usually the value of base resistor RB is greater than beta RE by a factor of 10. That is, RB is greater than or equal to 10 times beta RE. Therefore, we can also state that the input impedance ZI is approximately equal to beta RE, because if two resistors are connected in parallel, then the value of their equivalent resistance is always close to the value of smaller resistance. The output impedance Z0 for this system can be calculated by the formula of Z0 is equal to RC in parallel to R0. And if R0 is greater than or equal to 10 RC, then we can also say that Z0 is equal to, or rather approximately equal to, only RC by following the same argument as discussed earlier for the input impedance Zi. Now in order to calculate the voltage gain AV for this configuration, we need to first find the formula for output voltage V0 of this configuration, because AV is equal to V0 over Vi. The output voltage V0 is the voltage drop across the parallel equivalent resistance of R0 and RC, whose derivation can be found in the textbook. After performing simple mathematical steps, you will find that the voltage gain for the configuration is AV is equal to minus RC in parallel to R0 over RE. And if R0 is greater than or equal to 10 RC, then the voltage gain will be simply equal to minus RC over RE. These conditions have to be derived and have to be looked for while solving different examples related to these configurations. The negative sign in this voltage gain formula is implying that the input and output voltage for the common emitter configuration are always out of phase by 180 degree, as demonstrated in this figure. As you can see, there is a clear 180 degree out of phase difference in the input signal and the output signal. After all these derivations, now let us finally apply these derived formulas to get the values of important parameters of AC analysis in this example. After solving this example, many things will become quite clear to you. As you can see in this example, that we are asked to find the values of RE, input impedance Zi, output impedance Z0, and voltage gain AV for two different values of R0 for the given network. The network is shown in the diagram and the values are given. Before starting to solve this problem, always begin with redrawing the given circuit by its AC equivalent circuit by replacing all capacitors with short circuits, removing all DC supplies, and making the ground common as discussed in the previous slides. Here we will not derive the formulas again, rather we will just apply them to determine the desired values. As we know that RE is equal to 26 millivolt divided by IE, this formula was discussed in the previous chapter. Therefore, to calculate its value, we first need to find the value of emitter current IE. In order to get the value of IE, we need to perform DC analysis, that is, apply KVL on the input loop as we did in the previous chapter. You should not confuse yourself by this DC analysis, as unlike the DC analysis that only requires DC components, the AC analysis will always have some contribution of DC analysis, as AC associated DC components are always part of this analysis. As it can be seen that first the value of base current should be calculated by this equation. You must remember that this equation has come from applying KVL at the input side of this particular configuration. So after finding IB is equal to 24.04 microampere, we can simply find the value of emitter current IE by using the standard equation. IE is equal to beta plus 1 IB, and the value comes out to be 2.428 milliamperes. Finally, by applying the formula of RE is equal to 26 millivolt divided by IE, we get the value of RE, that is AC resistance, equal to 10.71 ohms as shown here. Once we calculate the value of RE, solution of part B becomes even simpler, in which we just need to replace the value of beta and Re to get the value of its product. Finally, input impedance is calculated by finding the parallel equivalent of Rb and beta Re, that comes out to be equal to 1.07 kilo ohms. This formula has already been derived in the previous slide, where we discussed about the RE model of a common emitter configuration. In part C, the output impedance Z0 is simply equal to the value of collector resistance RC, whose value is already given in the diagram. It must be noted here that Z0 is actually equal to RC in parallel to R0. But as the value of R0 is clearly greater than 10 times RC, therefore we can simply write that Z0 is equal to RC. This approximation has also been discussed on the previous slide. The same reason can be applied while solving part number D, in which we need to determine the value of voltage gain AV, whose actual formula is minus RC in parallel to R0 over RE. But as R0 is greater than 10 RC, therefore value of AV can be found by using the formula of minus RC times RE. That comes out to be equal to minus 280.11. This means that the input voltage Vi will be amplified 280.1 times, and the negative sign implies that the output voltage will be 180 degree out of phase, as discussed on the previous slide. In the last part, we are required to again solve part C and part D, but this time with a different value of R0 to make you learn about its impact on the amplification. As you can see that for part B, part C and part D, the values of R0 were infinity ohms. But now in part E, they are asking to solve these three parts again with a different value of R0, which is not infinity, rather it is equal to 50 kilo ohms. Now the value of R0 has been reduced to only 50 kilo ohms, and we are asked to include its effect in calculating Z0 and AV. As you can see that by including the effect of R0 in the calculations of output impedance and voltage gain, both of them are reduced. Z0 was earlier 2.3 kilo ohms, and after including the effect of R0, it has reduced to 2.83 kilo ohms, and the value of AV was earlier minus 280.11, but now the new value after including the effects of R0 is 264.24. So as you can see that both of them have reduced. So we can conclude that in order to make the overall gain value of AV greater, we need to increase the value of R0. Now let us analyze another configuration that is known as voltage divider bias configuration to perform its AC analysis for calculating the values of important parameters. We will be using the same RE model as of common emitter configuration as we have already used in the previous example. Now let us follow the similar steps as we did for the previous configuration of common emitter fixed bias configuration. As a first step, we need to redraw the given network diagram by removing all DC supplies and replacing capacitors with their short circuit equivalents. The redrawn circuit of the given network after incorporating the set changes and RE model of a transistor would look like the one as shown in this diagram. Here we have removed all DC sources. We have replaced capacitors C1, C2 with their short circuit equivalents, and we have also included the RE model of a transistor in this new diagram. again I would like to tell you that this blue color is used in this box again to signal or to imply that this blue box is representing the transistor equivalent model, and the equivalent model is still the same. On the input side of a transistor there is a resistor connected to it with the magnitude of beta Re. Then on the outer side or outer terminal we have two things, two electronic circuit elements, including a constant current source with the magnitude of beta IB and a resistor are not connected to it. The remaining circuit is the same. As you can see, RC is connected still at the output terminal. R1, R2 connected in parallel to the beta Re combination, as you can see here. Although R1 and R2 are not in parallel, but once we will short circuit this capacitor, then both of them will become in parallel to each other. Observe that all the grounds have also been made common like the previous configuration. You can also see that the output side of this configuration is exactly similar to the previous configuration, which implies that the formulas for Z0 and AV will stay the same. In order to derive the formula for the input impedance Zi, you should observe that the combination of R1, R2 and beta Re connected in parallel to each other will have an equivalent input impedance Zi. Therefore, the input impedance will be the equivalent resistance of R1, R2 and beta Re connected in parallel to each other. Equivalent of R1 and R2 is represented here by R dash, as you can see here. So R1 and R2 in parallel is represented here by R dash, and that R dash is connected in parallel to beta Re. R dash can be easily calculated by using this formula of two resistors connected in parallel. As I have already stated that there will be no change in the formula of output impedance Z0 and voltage gain AV for the voltage divider bias configuration, because the output side of this circuit is similar to the output side of common emitter fixed bias circuit. You can refer to previous slides for comparison. Therefore, Z0 is equal to RC in parallel to R0 and AV is equal to minus RC in parallel to R0 divided by Re. But if the condition of R0 is greater than or equal to 10 RC is satisfied, then Z0 becomes equal to RC and AV becomes equal to minus RC over Re, as shown here. Take care of yourself and your family and stay home.